part A, divide and simplify, we want to take the square root of 800x and divide by the square root of 8x. We have separate square roots divided. What could we do? I mean, I suppose I could simplify the square root of 800x, couldn't I? In other words, the 800 factor. I could definitely simplify that, right? Factor it as 100 times 8. Factor the 8 a little more, and I could pull out the perfect squares. There's an easier way to do it, though. Because we have an 800x in the radicand in the numerator, and we have an 8x in the radicand in the denominator. If we could make a fraction out of that, 800x divided by 8x, that would simplify, wouldn't it? Even though you might get it right, you're not allowed to cancel across a square root. You're not allowed to say, oh, that equals 100, because it's going to lead you in the wrong direction in the long run. What you need to do first is use that big property and combine it into a single radical. Okay, so I want to see this step first before you start canceling stuff out. The radicals do combine into one big radical as long as the operation between them is division or multiplication. And so we could rewrite it as the square root of 800x divided by 8x, and then look how nice it simplifies. What does that become? Just the square root of, the x's cancel, 8 goes into 800 100 times, you get the square root of 100. I'll go ahead and write that down. I think we know that that's equal to 10. So that simplified really nicely. Now, had you done it the other way, had you tried to simplify the square root of 800x first, it would have been a mess, huh? You could have got the right answer, but it just would have been messier. Here we have the cubed root of 135x to the 6th times y to the 7th divided by the cubed root of 5x cubed y squared. Similar idea here. Okay, what's the rule then? Well, if you have two separate square roots and you're dividing them, and you see like factors, like powers, like bases. We got powers of x, powers of y. Heck, 5 even goes into 135, doesn't it? When you see that, the easiest way to go about a problem like this is to combine into one big radical, simplify the radicand as usual by canceling, right? Canceling out like factors. And then wait and simplify the radical at the end, okay? So because you see like factors, combine into a single radical and simplify. Before you simplify the radicand, before you worry about simplifying the radical. So what do we, just to write it down, one big radical, one big cubed root, 135 x to the 6th, y to the 7th, divided by 5 x cubed y squared. Okay, how many times does 5 go into 135? 27. And then what's x cubed divided into x to the 6th? What's left over? X to the 3rd on top. And then y to the 7th divided by y squared? Y to the 5th. And that's all in the numerator, right? The entire denominator went away, didn't it? So I don't need to worry about saying over 1 or anything. So I have the cubed root of 27x cubed y to the 5th. Does everybody buy that? Now you can simplify, can't you? In fact, it simplifies pretty nicely. 27, do you need to do anything to that? It's a perfect cube, isn't it? X cubed. Perfect cube. Y to the 5th, oh, that blows it, right? So it's not quite, the radicand is not quite a perfect cube as one object, is it? So these individual factors, 27x cubed, are perfect cubes, but how do I need to factor this guy, the y to the 5th? Y cubed times y squared. Okay, so circle your perfect cube factors, this guy, this guy, this guy. Take their cubed roots, third roots, and write them as factors on the outside of the radical, and I'll just do that in a separate step this time. What do you get? Cubed root of 27? 3. Cubed root of x cubed? Cubed root of y cubed? And then what's left? Cubed root of y squared. There you go. You don't have to worry about absolute values when it's an odd indexed root, right? So none of that. I mean, that worry is not there anyway because our working assumption is variables are non-negative, but for odd roots, you never have to worry about it.